Hello everyone. In this lecture I shall discuss the dynamic programming which was introduced by Richard E. Bellman. Also the credit of another mathematician cannot be ignored in 1950. Okay, this Bellman together with another mathematician G.B. Danjing. Right. So jointly this G.B. Danjing and Bellman introduced this dynamic programming problem, but the credit goes to the Bellman. Accordingly, this principle work with the Bellman's principle of optimality. Okay, so now this dynamic programming problem is a mathematical technique dealing with the optimization of multi-stage decision process. Means a complicated programming problem is there. It is subdivided into different sub problems, and each sub problem is called the stage, right? And each stage is accompanied by some variables, right, to understand the characteristic of the stage, and it is called the state variable. Okay, so now, so this, as I have told, this stage and state, these are the two basic concepts which is necessary to describe the dynamic programming problem. So mathematically, how to work with a dynamic programming problem? Mathematically, a DPP, dynamic programming problem, is a decision making problem in n variables, right? In n variables. The problem is subdivided into n sub problems. Okay, n sub problems, as many as decision variables, as many as your sub problems, and each sub problem is known as the segment or the stages of the problem, and each sub problem being a decision making problem in only one variable, right? In only one variable, and this is called the state variable, right? So thus the solution of the LPP involves two basic concepts, as I have told. One is stage, other one is state, right? So what is a stage? A DPP is splitted, subdivided into sub problems, and each sub problem is called a stage, right? Now in each stage we have to take a best decision, optimal decision out of all possible alternatives, and the decision may or may not be optimal, right? But it will helps for optimal solution of the entire problem, right? So the optimal solution of the problem is accompanied by the solutions obtained from the individual stages, and basically from the first stage, right? Now what is state? State, it is a variable, right, that the decision which describes the condition of the decision process and summarizes the current status of the problem, which is known as a state. Basically it is a variable, okay, that describes the recurrence relations. So at each stage the problem is characterized by a set of variables or parameters, right? Otherwise it is called the state variable, right? Now before the further discussion in this regard, let me to introduce myself. Professor S.K. Paikray, currently working as a professor of mathematics at Surendra University of Technology, Visut, Burla, Odisha, India. So without much delay, let us discuss one example how this stage and state can be understood, and subsequently the Bellman's principle of optimality on which the entire dynamic programming rests. Now in view of the stage and state, we can say that at each stage a decision is made at each stage that transform the current state, okay, the value of the parameter, into a state in the next stage. Okay, so the state variable connects one stage to other stage. For example, in a production planning problem, how much to produce, right, to fulfill our demand in each month, say how much to produce to fulfill our demand in each month, right? So here the months are the stages, right, and the states are the inventory level at the beginning of the each month, right? So the month is the your stage, right? and the month is your stage, and each stage means at the beginning of the each month what is the inventory level. So that is known as the state. The level of inventory at the beginning of each month is the state and the stage is the month, right? So what is the dynamic programming algorithm? So in dynamic programming algorithm, in step 1 we have to identify the decision variables and specify the objective function, and step 2 we decompose the problem into stages, right, and identify the state variables, and here we transform, right, the state variables which is a function between the state variables and the decision variables, right. We are taking one as a state variable and other are the decision variable, so it transforms, and this transformation is a function of state variable and decision variables, right. Then we write a recursive relationship for optimal strategy, right, and we determine overall policy or decision and its value at each stage, and consequently we find the optimal solution, right. So this is the algorithm. Once we solve some problems, then your idea will clear. Now coming to the most awaiting thing is the Bellman's principle of optimality, which states as follows. Now this principle states that whatever it states that an optimal policy means set of decisions has the property that whatever the initial state and decisions are the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. As I have told you, in dynamic programming we have to take decisions at every stage, okay. So at initial stage we have a state and we have a decisions. So the optimal policy has the property that whatever the initial state and decisions, right, the remaining decisions must constitute an optimal policy and with regards to the state resulting from the initial decision, okay. So this is the Bellman's principle. Now we shall solve the linear programming problem by using the dynamic programming technique, right. In linear programming problem, what exactly it happens? It is a iterative technique, okay, and whatever the decisions is taken, it will continue throughout. But here in DPP we are to dynamic enough. It depends upon the individual stage with respect to the time, okay. So now we will discuss solution of LPP using dynamic programming technique. Right, dynamic programming technique. And one more thing, we write the recurrence relationship for optimal policy and we use forward or backward computation method. So here after we write the recurrence relation, right, we have to decide whether forward computation or backward computation to, and decide forward or backward computation technique to be adopted. Okay, so here we will solve the linear programming problem by using dynamic programming technique. We may adopt the forward computation or backward computation looking into the given problem. So let us solve some examples. So you are given a linear programming problem. This is an LPP you are given. LPP you are given and you have to solve it by dynamic programming technique. Okay. So here we have two decision variables. So these problems involve two stages. Okay. Suppose we select the forward computation method. Forward computation method means we use the first variable x1 as the initial variable, state variable, and we proceed. Okay. So here first we find the range of the decision variables, right? We have the range of x1 is equal to, you see here in this equation we have x1 is equal to 24 minus 3x2 divided by 2, and in this equation the coefficient here is 1, so it is here 6 by 1, right? 6 by 1. So to have a common solutions we should minimize it. Okay, minimum of this 2. And what happens to the range of x2? Range of x2 is equal to, here likewise the minimization of, from this we have 24 minus 3x2, right? Sorry, minus 2x1, 24 minus 2x1 divided by here 3, means we solve x2 here, and in the second equation we have here 0x2, right? So it is here 6 by 0, right? So for basically for x intercept we put y is equal to 0, so this is my 0, right? So it is my minimization of 12 and 6, 12, this is 12 and this is 6, so this is equal to 6, and this is minimization of 8 and infinity is here 8. Okay, so therefore what is my range? 0 less than x1 is less than equal to 6 because x1 x2 positive, and 0 less than equal to x2 less than is equal to 8. So this is my range of x1 and x2, right? This is my range of x1 and x2, right? Now come to stage 1. So here stage 1, it is forward computation, so we start from f1, b1, b2. So b1, b2 means two allocations are there here. If there will be more than two constants, accordingly we can take b1, b2, b3. These are the resources. Okay, so here b1, b2 is equal to, out we have to maximize this. So from this, at the beginning we are taking this x1 as the state variable. It is maximization of 3x1. So this is equal to my 3 maximization of x1. So that is equal to, I write, suppose the maximized value is my 3x1 star. So how this x1 star can be computed? Okay, this can be computed based on these constraints. So this is 3 here minimization of, right? This common out of these two, here minimization of, as I have told you, here x1 will be 24 minus 3x2 divided by 2, and here it is 6. It is 6 only, right? We have to find it. Now this x2 become a state variable for the next step, right? So now let it be my equation A. Okay, now this x2 is a state variable for the next step. Now what will happen in my stage 2? In stage 2, so in this stage we have x1 is the state variable. So we use the range of x1 here, right? In stage 1 we have x1 is the state variable here. state variable. So we use here the range of x1. The range of x1 is, we have 0 less than equal to x1 less than is equal to here 6. Okay. Now this x2 is a state variable in stage 2 x2. This x2 is a state variable here. State variable here. State variable. So what is my f2 b1 b2, right? So we have to maximize this objective function. We will start from 4x2. Okay, and this x1 will be computed from equation A, right? So this is equal to maximization over x2, right? It is 4x2 plus 3x1. This 3x1 star, this x1 maximized value as from the initial decisions we are taking. So this is equal to, the range of x2 here is 0 to 8, 0 less than is equal to x2 less than is equal to 8, right? So we write it. So this is equal to maximization over x2, right? It is 4x2 plus 3. What is my x1 star? It will come from this. Okay, so this is 3 minimization of here 24 minus 3x2 divided by 2 and 6, right? And 6. So now if you solve this 2, right, this is equal to this, then what will happen? If we simplify it here, right, if I solve this, then what will get? Here 3x2 is equal to 24 minus 12. 3x2 is equal to 12. So my x2 is equal to 6, right? So from 0 to 8, we have an intermediate value. So we write it maximization over x2, it is 4x2 plus 3, right? Minimization of, we have again two range, one intermediate range is 6, 0 less than your x2 less than is equal to your 6. One more thing, 3x2, it is 4, right? So it is 4. So here again this 4 less than equal to your x2 less than is equal to your 8, right? So in that way we will split. So what to write in which place, right? Out of this 2, at 4 both will give the same value, but at 8, this is your 6, at 8 it is 24 minus 24. So at 8 it is 0, right? So we write it here. This is my 24 minus 3x2 by 2, because it is giving the minimum value, right, at 8, but at 6 both will give the same value, at 4 both will give the same value. So it is 6 here, right? So that is equal to, you will able to write it. So it is 0 less than equal to x2 less than is equal to 8. So this is equal to maximum of, it will be equal to maximum of here 4, we are putting 4 here, 4 into 4 plus here 3 into 6, this is at, right, this is at here x2 is equal to 4, and it will be at x2 is equal to 8, it will be, or we may write like this, it will be here 4 into at x2 is equal to 8, it is 4 into 8 plus 3 times putting 8, this becomes here 0. So at x2 is equal to here 8. So maximum of our x2. So this will give you, this will give you maximum of, it is 16 plus 18, 34 and here 32. So it is the maximum value is 34. So the 34 maximum value at x2. So this is the optimal value of x2 is equal to 4. So now the value of x2 is obtained. Next I have to find the value of x1 star. Now this x1 star will be obtained from here. Now from equation A, right, x1 star is equal to your minimization of 24 minus 3x2 by 2, 24 minus 3x2 by 2, comma 6. Now putting this x2 star, I can write it x2 star. So is equal to minimization of 24 minus 12 divided by 2 and 6. So this is equal to minimization of 6 and 6 is equal to here 6. So hence what is the optimal solution? Hence the optimal solution is Z max is equal to 34 at x1 star is equal to 6 and x2 star is equal to 4. If we substitute x1 6 and x2 4, you see here, right, 6 into 3 18 plus 4 into 4 16. So this is the optimal solution. If we solve this problem graphically also by using your linear programming technique, you will get the same answer. Let us solve one more example. Now coming to the solution of question number 2, first we find, here we prefer to use the suppose backward. However, we may use any of the method, but since x2 is explicit, I prefer the backward, right? Backward computation I use, computation method we use. So what is my range of x1? So range of x1 will be from this, it is minimization of x intercept putting y0, it is 25 by 2, and here it is no x1, so it is 11 by 0, right? So it is minimization of 12.5 and it is infinity is here 12.5 and what about here x2? Range of x2 is equal to minimization of here the y intercept putting x is equal to 0, it is 25 by 1, and here the coefficient 1, x2 is 11 by 1. So this is equal to your minimization of 25 and 11. So this is equal to your 11. Okay. So now my stage 2. At stage 2 I start with F2. Okay. B1, B2. Two resources here and two decision variables. That's why it is a two-stage problem. So this is equal to, we will start from the second variable, right? We will start from the maximization of 9 x2 and here x2 over x2 ranging in the interval minimum is 0 and it is here 12.5, right? So this is equal to, I can write 9 maximize 9 I say suppose it is the maximized value is x2 star. Okay, 9 x2 star. So this x2 star is my 9 common out of this 2, right? Common out of this 2. So 9 minimization, how to find here x2? So here what is x2? It is 25 minus 2x1 and here x2 is equal to here 11. Now this at this stage, what is my state variable here? The state variable is x2 is my state variable. X2 is my state variable in this stage. Okay. Now for the next step, this x1 will be the state variable for the next step, right? So now we write stage 1. At stage 1 we have F1, B1, B2. Okay, F1, B1, B2. So we have to start from x1 here. So it is maximize x1 plus 9x2, right? It is maximize over x1, right? It is x1 plus 9x2, right? This x2 here is my x2 from the previous step. So I write x2 star here, and this x1 ranges from 0 to 25 by 2, right? So now I substitute here. So this is equal to maximize over x1 and it is here x1 now plus here 9 x2 is the minimization of this. X2 is here minimization of 25 minus 2x1 and 11. Okay. So now if you compare these two, this is equal to this, then what is the value of your x1? If you simplify, this is equal to this. So my 2x1 is 14. So my x1 is my 7 here. So this x1 0 less than x1 less than 25 by 2, okay, 25 by 2, but the intermediate value x1 is 7. Accordingly we split it. So this is equal to maximization over x1. It is x1 plus 9 times, it is within one range 0 less than equal to x1 less than is equal to 7, and again in another range 7 less than equal to x1 less than is equal to, here final value is 25 by 2, 25 by 2. So now at 7 both will give the same value, at 7 both will give the same value. So now you see at 7 this and this will give the same value. So first we have to write here at 25 by 2, this is 11 but this is 0, so this is minimum. So we write this value here, 25 minus 2x1 here, and the other value 11 is here, right? So this, so now we simplify it. So this is equal to maximization of the value of x1 is 7. So this is 7, this is 7 plus 9 into 11, 9 into 7, 9 into 11, 9 into 11, right? And it is 0 less than is equal to x1 less than is equal to 7, or I can say at x1 is equal to 7, okay, at x1 is equal to 7, and here it is 25 by 2 plus 9 into, right, this is at 25 by 2, it is 25 minus 25, it is here 0. So at x1 is equal to 25 by 2. So this is equal to maximum of, this is 99 plus 7, 106, comma, this is here 0, 12.5, 12.5. So this is, you are getting 106, but 106 at which value? At x1 is equal to 7. So at here x1 is equal to 7 here. So my right, this is the optimal value of x1 star. Now let it be my equation A, okay, let it be my equation A. This equation A will give you, this is your equation A. This equation A will give you the value of x2 star, okay. Now from equation A, right, now from equation A, here x2 star is equal to minimization of 25 minus 2x1 star, 25 minus 2x1 comma 11. This is x1 star I will take, so I substitute this here. So this is equal to your minimization of 25 minus 14 and 11. So this is equal to your minimization of 11 is equal to 11. So therefore what we conclude, the optimal solution is Z max is equal to 106 at x1 star is equal to 7 and x2 star is equal to 11. So this is your answer. Now let us solve one more problem. Now coming to example 3. So here we can adopt any of the method, forward or backward, okay. Suppose we adopt forward computations. So in backward computation we should write from the last stage, we did it. So in stage 1 here we have x1 is the state variable here is here x1, okay. So now here we have forward computation we are using. So range of x1 is equal to, and range of x2 is equal to. So range of x1 is from this is minimization of 12 by 2, 12 the coefficient here this 2, and it is here 8 by 2. So this is minimization of 6 and 4 is equal to here 4, and here x2 is minimization of, it is 12 by 3 from the first equation, it is 8 by 1 from the first equation. So this is minimization of 4 and 8. So this is equal to here 4. Now since it is a forward computation, we start from stage 1 with x1 as the state variable. So in stage 1 we have first x1 Okay, maximize 6x1, maximize 6x1, and ranging our x1, and x1 is 0 less than equal to x1 less than is equal to 4. This is equal to, I write maximization over x1, 6 taken out, it is x1 star. So what is my x1 star? It is equal to 6 minimization of x1 out of these two equations. Out of your equation 1, x1 is 12 minus 3x2 by 2, and out of this equation 2 we have second constant, we have x1 is equal to 8 minus x2 by 2, 8 minus x2 by 2. Now this x2 will work as a state variable in the next step. Let it be my equation A. Okay, now coming to my stage 2. In stage 2, this x2 is my state variable, x2 is my state variable, right? So what we have to do, it is maximization over x2, and we start from x2 first. 7x2 plus 6x1, 7x2 plus 6x1. This x1 is out of this previous stage, so x1 star, right? And x2 ranges from 0 to 4, 0 to 4. So this is equal to, I can write maximization over x2, it is 7x2 plus 6. This will be substituting A here, minimization of 12 minus 3x2 by 2 comma 8 minus x2 by 2. If you simplify this 2, what is the value of your x2? So now if you solve this, your 12 minus 3x2 is equal to 8 minus x2. So your 2x2 is equal to your 4, implies x2 is equal to 2. Okay, so intermediate value, the range is 0 to 4, but there is an intermediate value 2. So we should write it maximize over x2, it is 7x2 plus 6, minimization of intermediate value is 0 less than x2 less than 2 and 2 less than x2 less than 4. So out of these two we see at 4 which one is minimum. Okay, at 4 it is 12, it is 0, it is minimum. At 4 it is here 8 minus 4 2. So this minimum value should be written over here, 12 minus 3x2 divided by 2, and this value 8 minus x2 by 2, this value is written over here. Okay, now we simplify it. So this is equal to maximize over x2, right? It is 7 into substituting this value 2, 7 into 2 plus 6 times, it is 8 minus 2 by 2, 3, right? 3 at x2 is equal to 2, and here it is 7 into 4 plus it is here 0 at x2 is equal to here 4, right? So this is equal to, you can write maximization of, it is 14 plus 18, it is here 14 plus 18 is 32 and it is 28. So this maximized value is here 32, but this 32 at which point? This is subject to this at x2 2. So this is the optimal value of x2, I write x2 star. Now I substitute the value of x2 here, right? I substitute the value of x2 here. Now from equation A, my x1 star is equal to minimization of 12 minus 3x2 by 2, 12 minus 3x2 star by 2, and it is here 8 minus x2 star by 2, 8 minus x2 star by 2. So this is equal to minimization of 12 minus 6 by 2, 8 minus 2 by 2. So this is minimization of, it is 6 by 2, 3, and it is 6 by 2, 3. So this is equal to 3. So therefore my optimal solution is Z max is equal to 32 at x1 star, right? At x1 star is 3 and x2 star is equal to 2. So this is your answer. Okay, now let us solve one more problem where there are 3 constraints. Okay, so we have 3 allocations here, means b1, b2, b3, but 2 decision variables. So it is just 2 stage problems here. So now we may adopt forward or backward. Suppose I adopt backward computation. You may adopt forward, no issue. So what is the range of x1? Range of x1 is, it is minimization of, here it is 4 by 1 and here there is no x1, 6 by 0 and here it is 18 by 3. Okay, so this is equal to minimization of 4 infinity and 6 is equal to here 4, and range of x2 is equal to likewise the minimization of, first one is there is no x2, so 4 by 0, second one it is 6 by 1, third one it is 18 by 2. Okay, so minimization of 6 and 9 is equal to your stage 6. So since we are adopting backward computations, so at my stage 2 first, last stage 2, what it is my f2, b1, b2, b3, 3 resources, 3 constants. Okay, so I have to work with second variable, means 5 maximization of 5 x2 over x2, right? So this is equal to 5, I suppose write it x2 star. So now this x2, the range is 0 to 6, 0 less than x2 less than 6, so I can write it. So this is my 5 x2 star is minimization out of this 3, so it is better to take this 2 because there is no x2 here. So it is minimization of here x2 is equal to 6 here and x2 is equal to here 18 minus 3 x1 divided by 2. Let it be my equation A. Now this x1 is a state variable in the next stage. So here it is x2 is the state variable. Now coming to your next second stage, here stage 1, actually stage 1 we are computing backward from the last. So my f1, b1, b2, b3 is equal to maximization. What is the stage variable here? State variable x1 is the state variable. So we start from x1 here. Okay, it is maximization of 3x1 plus 5x2, but 5x2 already x2 the optimal value we have considered. Okay, and what is the range of here x1? Here x1 is ranging from here 0 to 4, 0 less than x1 less than 4. So this is equal to, I write maximization over x1, it is 3x1 plus 5, I have to write this value, it is minimization of 6 and 18 minus 3x1 divided by 2, right? So x1 ranging from 0 to 4, so I have to find a intermediate value. Now if I compare, so this will give me x1 is equal to 2 here, right? So we have maximization over x1, it is 3x1 plus 5, we have a intermediate value here, 0 less than x1 less than 2 and 2 less than x1 less than 4. So at 4 this will give you, so this will minimum at 4, right? So it is here 6 is here and it is 18 minus 3x1 by 2, right? So this is equal to, I can write maximization of, and it is my at 2, it is 3 into 2 plus 5 into 6 at x1 is equal to 2, and it is 3 into 4 at 4 plus 5 into substituting 4 here, 18 minus 12, 6 by 2 3 at x1 is equal to 4, right? So this is equal to, I can write maximization of, this is 36 and it is 12 plus 15, it is here 27. So out of this 2 the maximum value is 36. So 36 at x1 is equal to 2. So this is the optimal value of x1. Now if we consider equation A to find x2. Now from equation A, now from here A, here x2 star is equal to minimization of this, minimization of 6, 18 minus 3x1 by 2, 6, 18 minus 3x1 by 2. So this x1 is this x1 star, right? So this is equal to minimization of here 6, 18 minus 3 to just 6 by 2. So it is minimization of 6 and 6 is equal to 6. right? So therefore optimal solution is Z max is equal to 36 at x1 star is equal to x1 star is equal to 2 and x2 star is equal to 6. So this is the answer. Okay, this is the answer. The video is getting lengthy, we should close it here. So to summarize the DPP, dynamic programming problem, it is dynamic in the sense that we are taking intermediate decisions at every stage. So multiple problem is splitted into sub problems to get the answer easily. Okay. However, in linear programming problem, whatever the initial decision is taken, it is carried throughout. Okay. So now at this juncture, my appeal to all of you is that if you feel this lecture is interesting and helpful, please like and subscribe to this channel. Which will boost my motivation to upload subsequent lecture. In my upcoming lecture I will solve solution of NLPP, solution of non-linear programming problem, NLPP, by using DP technique. Okay, so with this we should close this lecture here. Thank you all. Have a nice day.